We'll start with the Hedera SDK for JavaScript. So if you're following along with the tutorials, then what you'll need to do is go back to the docs folder and navigate to this one over here and follow along. So this is what we'll be doing here. Now, back to the repo. So the Hedera network offers multiple services: smart contract service, file service, token service, and consensus service. And each service has several different ways that you can interact with it. But these interactions, like as they are exposed, they are actually something called HAPIs or Hedera APIs. And working with them is very low level and definitely beyond the scope of this tutorial. So instead of interacting with it at such a low level, Hedera provides a set of SDKs in different languages. The one that we'll be using today is the JavaScript version of that SDK. And we will use that SDK to essentially work with the Hedera Smart Contract Service, or HSCS. All right, so the first thing we want to do is let's go into the terminal, go out of the intro folder and go into the Hedera SDK.js folder, and then let's do an npm install. And wait for that to finish. So the first thing that we're going to do once that is installed is to actually compile the smart contract. So this smart contract that we've written here, we actually haven't done anything with it. We've just written it as a text file, and it isn't actually doing anything, so to speak. And now we're going to start using it for the first time. So by way of intro, you can see the trogdor.sol file here. And now in the Hedera SDK.js, we've got some files prepared here, but you can see the smart contract that we have is empty. And I've also left in almost empty files here for expected outputs from the smart contract compilation. But these are basically an invalid ABI, invalid binary file, and an empty smart contract. So that's our starting point. And we also have several scripts which we will be completing later on. So the first thing we want to do is we want to actually have this smart contract. And we're not going to write it from scratch. Instead, we're going to just do a copy from the intro to Hedera SDK.js /trog, and then we want to copy it to this folder. So now, if we open up this file over here, we can see that in Hedera SDK.js, this file here exists, right? Same content as what we had in the intro. And that's what we wanted. Okay, that's the first step, copying smart contract. Now, the next thing is that we need the Solidity compiler. So npm install. Okay, there are several ways to install the Solidity compiler. I think the one that I find the easiest is the npm route, but you can check out the documentation from Solidity Lang to find several others. All right, so I already had this version of Solc installed, but it'll be a bit slower if you're doing it for the first time. Now, note that the binary that it installs is not the same as the package name. That's Solc, that's Solc.js. That's the main thing that you need to be aware of. Now, if you issue a command to output its version, you can see over here, that's the version number, the specific git commit, if you wanted to find it on the Solidity GitHub repo. And importantly, this bit here tells you that it's been cross-compiled. So this is not the original Solc, but rather the version of it that's been cross-compiled using Unscripted and therefore converted into JavaScript. And that allows us to install it in the way that we have. And it's a bit more convenient to work with using tools such as Truffle Hardhat, which we will happen to use later on. All right, so, okay, we have got a version of the Solidity compiler. So now let's just see what it can do. So this is a fairly simple tool in terms of the interface that it exposes. The number of flags and options actually fits into a single screen terminal, which is not the case in most Unix tools. A lot of options here, but the ones that we're really going to be using are these two, bin and ABI. We want to output the EVM bytecode, and we also want to output the ABI as a JSON file. So these two are the ones that we'll be using. So now these two files, let's just remove them actually. You don't have to, but I'll just do it just for the sake of demonstration. So those are the ABI and bin files that I have from my previous usage of the compiler that I've just deleted. And so what we want to do next is to actually run the compiler. Moment of truth, was our smart contract valid? Did we write valid solidity syntax? So bin, ABI, and this file that we have here is trogdor.sol, and we're going to compile it, and we're instructing it to output both the EVM bytecode and the ABI JSON. Right? And now to ls, we can see that these files have been generated again. So let's take a look at them. So the bytecode is this basically massive long string of hexadecimal text. Nothing much to really read into this, really, because it's literally not meant to be human readable. Just the most important thing to check really is that the output has indeed been created. Now, the next thing of interest is the API output. Now, this one here is actually valuable. Now, it outputs it in this very dense format that's kind of hard to read. So if you happen to have the JQ tool, I recommend that you do this installed. And if you're on Mac, you can just install this via brew, or if you're on Linux via apt-get, I believe. So trogdor.sol.abi. So it really is a JSON file. So then you can get this, syntax highlighted, parsed version of the JSON file, and you can see how this actually corresponds to the file quite easily. For example, you can see that it has a burnination event, and the parameters are an address and a uint of 56, for example. You can see that it has a payable function called burninate, and it has no parameters, and it has no return value. Total burn has no inputs, but it does have a return value of type uint256, etc. So this ABI does give us a pretty good idea about what the smart contract is and what its exposed interface is, and is definitely intended to be human readable. All right, so we have just successfully compiled our smart contract, and that's step one. So step two is to deploy the smart contract, and then step three, we can interact with the smart contracts, and that's the sequence that we'll be going through. So let's open up the deploy smart contract file over here. So we've got this file that's been prepared for you, just like we did with the solidity file, and you can use the same sort of steps to interact with it. Sorry, to follow along with the tutorial using the step ID identifiers over here. So the first thing we want to do is to initialize the operator account. To do that, and to do many of the other interactions here, we've imported the Hedera SDK for JavaScript. And this is a required statement. And here are the classes or objects that help us do what we want. So the first thing we're going to do is create an account ID. String. And then we want process.env.operator ID. And let's just quickly understand how that actually happens. So this file here, .env, reads in the .env file that's in the root folder of this, one level up. then that's reading in operator ID. And the .env library sets that and under the environment variable, and that's why it's accessible under process.env. So that's what's going on. And then we'll use the same sort of thing, but this time we will initialize a private key with a different environment variable. Start from string. And then we'll also get process.env operator key. Okay, we've read those two in, and then after that, initialize the client with a default testnet configuration, and then set the operator account as being what we just initialized using those environment variables. So subsequently, we can use this client to issue all of the network interactions, and that's what we're doing right in the subsequent steps. The next thing is we need to read in the bytecode file. So this file over here oops, I want the bin. So this code here is what we want to send onto the Hedera network and use this to create a smart contract. The ABI is just for us to know how to interact with it, and that stays in the client side. The binary file, the EVM bytecode, the one that we cannot read, that's the one that actually goes onto the network. All right, so EVM bytecode, what do we want to do here? We want to read the thing from disk, so it will be fs.read file. And then we need to specify the name of the file. So let's get that. All right, then the next thing we want to do, we can't, using the SDK, the Hedera SDK, we are not able to directly deploy that with a deployment transaction. There's actually a prerequisite step, which is that we put it onto the Hedera file system first, and then subsequently we say, hey, Hedera smart contract service, check out this file on Hedera file service. Okay, go and deploy that. So that's essentially what the sequence that we're going to go through now. We're going to do file create transaction. And this is essentially a Hedera File Service API. And then we're going to do set contents. So the file create transaction contains basically the binary file that we just read in. Then once we prepared the transaction, we actually need to put that onto the network and check that the network has executed it. So file create dot execute. And then file create transaction dot get receipt. So once a transaction has been executed, we have to wait for it to complete, and then we get a receipt for that transaction, which contains the detailed information about the transaction and its completion. Vitally, what we're interested in the receipt is this property called file ID, because we need to use that subsequently when we are telling Hedera smart contract service about what to deploy. So now we are going to reference the EVM bytecode that's been stored on Hedera file system using that file ID. So for this, we're going to need a contract create transaction. And then we're going to say that where the bytecode is located. So set bytecode, file ID, and then specify the file ID. And then we're going to say set gas. So you have to pay for the transaction using some amount of HBAR, and that should cover it. Okay, next up we have a deployment transaction. So smart contract deployment dot execute. Right? So we prepared that transaction here, but it hasn't been sent to the network. This actually sends it to the network, and just like before, we are going to get the receipt. And the receipt will contain the contract ID, which we are then going to output into the console. Okay, I think we're ready to run that. So node / deploy smart contract. And let's run that script. Wait for it to do its thing. All right. So we can see here, HFS file create transaction. Here's a transaction receipt that has been output. And we do indeed have a file ID, this object over here. Then subsequently, Hedera Smart Contract Service, contract create transaction, and we have its transaction receipt. And we have its contract ID, which is this object. And then parse that and output it as a string. All right, so we could just take its word for it that this has worked, but let's not do that and go to Hashscan and verify it that's actually live in the ledger. So again, hashscan.io, check that you're on testnet, and then put that, copy that from the output, paste it over here, and you should get to a contract page. Now, if you say a page that says not found or something to that effect, it basically means that the deployment transaction did not succeed. So definitely you do want to check that. All right. So what do we want to do here? So we get a contract page, and I think the one interesting thing here is that you see that it has an EVM address. Now you'll notice something like a little bit strange or funny. In EVM addresses, you're not used to seeing like a whole bunch of zeros preceding a number at the end. In Hedera, this happens, and it happens when you deploy a smart contract via the SDK and calling the contract create transaction directly. Now, if you do it in a different way, via the Hedera Smart Contract Service directly, and we'll see that in a subsequent step when we're using hard hat and HSCS, you'll get a different type of address. So in Hedera, we refer to this as an EVM address, but specifically we call this the long zero EVM address, as opposed to a non-long zero EVM address. And then the other thing that you'll see is contract bytecode. So you'll see a whole bunch of hexadecimal text. Note that this is not the same as, you know, the bytecode that was output previously. And then the bin file. So this bytecode is quite similar to, but not the same as this, because this bytecode, when it is deployed, it is sent to the network, and then the network has to process this, and then whatever the outcome of the processing is, it gets output, it gets stored on the network. So not exactly the same, in case you happen to check that. But it is deterministic. This bytecode will always result in this bytecode. And I won't get into the details of why that's necessary or how that works, etc. That's beyond the scope of this tutorial. All right, interacting with smart contracts, the thing we want to do next. So we've already got a contract that's been deployed. How do we actually do stuff with it? So the key here is that we have this smart contract, and we have its ABI. So we know what the smart contract does. And importantly, we also have from the ABI, we know its function name. So we know that we can call a burn innate function. We also know that we can call a total burn function. This one updates state. This one doesn't update state. And also, because both of these are public, both of these variables, the Solidity compiler automatically generates accessor functions for them. So you can actually query amounts, and you can also query min fee if you want to. All right, so to do that, let's use another file that has been prepared earlier on called interact with the smart contract, interact SC. So this same pattern as before has been prepared, and we just need to complete a few critical steps that I want to highlight. So the first thing we want to do is to go right to the bottom in step F1 and copy the contract ID that we had earlier on. So copy that and paste it over here. So essentially, we're telling this script that we want to interact with this specific contract that we just deployed. You can give it any other contract ID if you want, as long as it effectively has the same ABI, it should technically work. All right, so moving on, we've got the next step where we initialize the operator account. Now I'm going to be a little bit lazy here and just copy paste. Right. And that should do it. So now we've got the operator count initialized, and then the next line we're going to do is we're going to actually interact with it. Now, let's see. So we're going to invoke the payable function, and we're intentionally going to do it with a 0 value just to trip up the require function, because we can see the implementation over here. We know that if we call this function and the value is 0 or anything less than 100 really, it'll just revert it. We're basically trying to trigger that and make that happen on purpose. So what do we do here? So because this particular function is public payable, we're going to do this where we do a contract execute transaction, right? And then we set contract ID. And then we set gas, pay for the transaction. This contract ID is the one that we passed in over here and was obtained from the deployment step that we just completed earlier on. And finally, we set function. And this is essentially identifying that the function name is burn-in. It doesn't take in any function parameters, so that's just fine as it is, empty. And then finally, we need to execute it. And then this will do a try and a catch in case of an error. So in this case, we're expecting it to catch and output an error. Now, the next thing is we're going to do it like sort of properly. So we know that we're going to send in a value of 123, which is more than 100, the minimum required for the min fee, and therefore that require statement should pass. So we've got a contract execute transaction. We're going to do the same thing, set contract ID, and then we're going to do set gas, same as before. The only thing that's new is that we're going to do a set pay dollar amount, right? And here we'll specify 123. Hey, but we don't want to send in 123 HBAR. We want to send in 123 tiny bar. So HBAR unit dot tiny bar. So note that the numbers here, like numbers here for anything that's sent in by payable and message of value, is denominated in tiny bar, not in HBAR. So that's how we get that here, right? And then set function. And again, we're going to call burn-in and with no parameters, and then we want to execute it. All right, so we've got essentially contract execute transaction happening twice with the exact same thing in both cases. The only difference is that set payable amount is 0 by virtue of it not being even called here, and here it's got a value that should satisfy the requirement. Now, the next thing that we're going to do is invoke a view function with no parameters, and that one is the total burnt function, right? So that's external view, if I remember correctly. So since this one is a view function and it doesn't update state, we don't want contract execute. We want contract call query. Yeah. So set contract ID, set gas, and then we set total burn, and it also doesn't require any parameters. And then we need to do set query. All right, let's do execute. And note that that you do have to pay for queries on the Hedera network. So it's not just transactions that need to be paid for that change state. All right. Okay, so this code here will actually run the query. And then in this case, we have a return value that we need to process. Now, in the smart contract, we can take a look at total burn, and its return value is of type UN256. The contract call query doesn't necessarily know that, so we just have to specify that we're going to extract get UN256 from it. All right. Now, the next thing what we're going to do is we're going to invoke the amounts function. So recall that amounts is a mapping, and since it's public, the Solidity compiler has automatically generated an accessor function for it. Now, this accessor function requires an input parameter of type address, and then its return value will be UN256. So that's what we're going to be querying next. But in order to do that, we need an address. And at this point in time, we don't have the address in this script, at least. We don't have the address of the account we want to use. So let's do that. So what we need to do is derive the public key from its private key, and then from its public key, we can obtain the EVM address. So let's do that. So operator private key dot public key. Oops. Let's just check that operator private key exists. All right, operator key is over here. Operator key dot public key, and you get operator public key. Operator EVM address dot public key is dot to EVM address. All right, awesome. All right, now we have the value that we can use as an input parameter for to invoke amounts. So now again, we're going to do another invocation of contract call query, right? Contract call query. And then we'll set the contract ID to ID, set gas, set function. And now there's something new, which is we need to specify a parameter or an input parameter for this function. So let's go ahead and do add address. And then finally, we can do set query payment. All right, we're ready to execute it. So at this point, this will call the amounts function, and then we're going to pass the return value, which happens to be UN256. So get UN256. All right. That's it. Right. So let's run the script. I think we're ready to run the script. So node/interact with smart contract. All right. So a lot of output here. Let's go through them one at a time. Oh. Receipt status error, contract execute transaction. I was not expecting that. So what was the very first one? Oh, okay, so this is indeed contract revert executed, and the reason for it is because we didn't send in a message value. So that's fine. Sorry, threw myself off there. All right, contract execute transaction number 2 to the transaction receipt. This one looks successful. Now, here's the interesting thing. Now we interact with the contract itself for number 1, which is for total burn, and that returns a value of 123, which is what we expected. Now, if you run this multiple times, this value will increase by multiples of 123. And then again, now we're calling the amounts, and we also have a return value of 123. Let's run the script a second time and see what the values are, right? Right, and this time, right, when we do the contract function results, we're expecting it to be more, right? 120 times 2, which is exactly what we've got. After deploying smart contracts, we have sent some transactions to modify its state, and then after that, we query its state, and we're getting the values that we expected. All right, and we also demonstrated a rejected transfer as well. This one over here, the first attempt to modify the smart contract state was essentially rejected because we ran into this require statement within the burn function saying, hey, you're not allowed to do it unless you hit this minimum threshold. Okay, so again, right, we could just trust the output from what you see on the terminal, or you could verify it, right? So what I'd like to do here is to actually get the contract ID, which I have over here, right? And search for that inside of Hashgraph. All right. And you should get to a URL that looks something like this, and it should be a contract page, right? Now, once you have this, right, you can scroll down to a section called recent contract faults, and you should see something like this. Let's see. Yeah. So sometimes if the page has been open for a while, right, to save bandwidth, it'll have this pause and play button. So make sure that you unpause it, essentially. Yeah. And then when you get down here, you can see your contract fault history, right? So this one here would have been the least recent one, would have been the deployment. And then subsequently, this would have been the first attempt to call it with the payable function, the burn function with the value of 0. And then you can see here the error message. And then the second one where it succeeded. Yeah. And then I ran the script 2 times, right? So the second time it did this, right? So again, error for pay at least minimum fee, and then subsequently a success, right? So there we go, right? So click on the row for the failed transaction and navigate to its transaction page, right? So this one, right? So you should see a transaction contract revert executed, right? And then if you see the scroll down to contract result, you see this pay at least a minimum fee, right? And you can get more details over here if you want. Now let's go back to the main page and go to the most recent call, which would have been a successful one, right? And you can see over here a few different things, right? So one of the things is transfers. You'll see that this account has decremented an amount of HBAR, and it has, gone to as a transfer to this other account. And this other account happens to be the smart contract. This is the operator account that has been interacting with it. So my operator account has essentially transferred some money into this smart contract. All right. The other thing is you'll notice within trogdor.sol, in the Solidity file, that it's been emitting this burn nation events. Now, let's scroll down a bit here and take a look at logs. And you should see a single entry in the logs. The address is the address of the smart contract, and the index field is 0, since there's only a single event. The topic essentially is a hash of the signature of the thing. So signature of the event, I should say. So burner nation address uint, you take that and you hash it and you get the topic. And it's a bit more complex than that, but that's the rough idea. And the data is essentially what's in it. So it should contain an address followed by a uint 256. And you can see here, and this is going to be pretty low level. You can see here the first half of it in terms of width, all the way up until that 4474. So I'll make this a bit bigger so it's easier to see. Let's see if I can get it to align nicely. No, that didn't work. Okay, so if you go from here all the way up until here, there's a bunch of padded zeros, but if you start from here to here, that's the address of my account. And then if you go from here up until here, that gives you a uint 256. And if you convert 0x7b into decimal, you should get 123 because that was the amount. So let's just do that. Convert 0x7b to decimal. 123. What's it called? Smart contract verification. And one of the things that means is that the page can have an ABI attached to it. And if it has an ABI attached to it, it'll be able to parse, for example, event logs. It can actually should be able to display to you that this event was a burner nation, and the data can say, okay, the address was this, and you wouldn't have to look at the raw hexadecimal values yourself. All right, so yeah, that's it for the Hedera SDK section of this tutorial.